Computers say no. Many of you will have heard that. And my bet is that if you ever use the computer, it will have said no to you at some point. It will have presented you with a problem. There is the dread blue screen. There is the situation when you're typing and nothing's happening. The screen is frozen. That's what I mean by the computer says no. It behaves in an unexpected and unhelpful way. What about robots? Can we trust that robots will always behave as expected? Can we trust that robots will always say yes to us? There is a lot of interest in robotics in the media. If you remember that autonomous vehicles are robots, I think that's clear. The UK government has identified 8 great technologies that will have a profound impact on our economy in the future, and robotics is one of them. There are several predictions for the size of the robotics market in the future, and they are all of the order of billions and billions of pounds. So what's going on? Basically, at the moment, robots are working normally in factories, inside cages, away from humans. But there have been extraordinary advances in electronics, in mechanics, and artificial intelligence, and we are now developing applications where the robots are coming to work near us, sometimes in collaboration with us, with humans. And robots can be very useful in environments where humans cannot be. Nuclear reactors, the deep sea, the space, but they can also be very useful near us. For example, a medical robot can operate with a precision that's not possible for the human hand. Robots have the possibility of improving our environment in offices, in hospitals, in airports. Robots have the possibility of providing assistive care for the elderly. Robots have the possibility of providing education and entertainment for our children. But in all these situations where the robots are working next to us, there is a concern about trust. There's a concern about safety, for example. If a robot is strong enough to help an elderly person to get up from a chair, the robot is strong enough to hurt that person, and we cannot have that. So, what can we do about this? What is the position that we are? There are several issues related to establish the trustworthiness of a robot. And what I'm going to talk to you about today are the issues related to the software that controls those robots. A piece of software is an engineering artifact, just like a car, or a building, or a laptop. But as a society, we have a very lax view of software. If a bridge collapses, there is a public outcry, most likely even legal action. If I buy a laptop and, I don't know, the screen is cracked, I want my money back or I want a new laptop. But if the software that's running that laptop doesn't work, I'm very happy to say, perhaps I need to reset it. Or perhaps there will be an update. And updates come over and over again. My whole career as a researcher has been about changing this situation. Why cannot software engineers provide the same sort of guarantees that a civil engineer can give, for example? What's the problem? Blame the tools, not the engineers. Our software engineering community is extremely successful. Our society depends on our software infrastructure very fundamentally these days. I'm guessing that most of you have a smartphone on you. You are carrying a lot of software on you. If you go and buy a pint of milk, you are relying on a lot of software infrastructure. All the way from the farm, farmers are using automated machines controlled by software to milk their cows. To the shop, when software allows you to pay for your milk, allows the shopkeeper to control their stock, interact with the delivery system that uses lots of lorries, where a lot of software is running. If the software infrastructure in our society overnight stopped working, society would go to a standstill very quickly. And this reflects the brilliance of our software engineers. So what's the problem? The problem is that they need models. They need to work with models, mathematical models that underpin their practice, just like any engineer. You cannot imagine, it's inconceivable to think that a civil engineer is going to start the project of a new building by laying some bricks. And laying bricks is to civil engineering like writing lines of code, writing programs, developing, actually creating the software, is to software engineering. That's not where you start. So a civil engineer, we know how they work. They write some plans, they build some maquettes, and they use those to discuss their design with their stakeholders, but also to analyze and predict the properties of their designs to make sure that the building is not going to collapse, that it's going to provide adequate service, water, electricity, and so on. And software engineers can work like that. The mathematical principles that underlie software engineering are already known. In many areas of application, they are used. The techniques based on these mathematical principles, which are called formal methods, are used very successfully. And the trick is specialization for the domains of application. And roboticists do not have the specialized techniques yet. How do roboticists work? Roboticists use extremely advanced techniques when it comes to the development of the electronics and mechanical aspects of their artifacts. When it comes to the software engineering, the practice is very outdated. They basically start by writing code, laying some bricks. Many start writing a simulation, and you could say a simulation is a model, but it's not a mathematical model that allows you to reason about your artifact. It is code, right? And so that's how they start, not using models. And in that situation, they may face problems, as you can expect if a civil engineer started laying some bricks. That's not how you do it. And what do they then have? The code is the only thing they have in hand. They write it and they try it. They try it on the robot, in lab conditions or in the real world if possible. It's not always possible. They observe the behavior. If there is a problem, they go back to the code, change, and try again, and again, and again. In the end, what can they say? What can they assert? All they can say is that I didn't find a situation where a problem occurs. They cannot say there is no situation where the robot is going to misbehave. They cannot even say these are all the situations in which the robot will not misbehave, and therefore these are the situations in which I can guarantee the behavior of the robot. They don't have that. For that, they need models. And what does a model for a software engineer look like? It looks like a recipe, a step-by-step description of what the software, of what the robot should be doing. And now, with this question of recipes, I'll run a parallel with my mother's recipe. I have to be very careful about what I say about my mother on the record. She has lovely recipes that she kindly shares with me, but they are not precise. They say things like, cook until it's a little brown, or put a pinch of salt. And often I have to call her and ask, what do you mean? Even worse, sometimes I don't realize that I have to call her, and here's what I get, instead of that lovely cake that I wanted to do. And roboticists have the same problem. Many try to write the recipe for their robot. Here's an example. I don't need you to understand the details of that diagram, but that diagram is an attempt for colleagues. This is taken from a paper in the area of robotics. It is an attempt to describe the recipe, the step-by-step behavior of the software for their robot. But it's not a model. It's not precise. It's not backed up by mathematics. We tried to use that, and we couldn't understand what that diagram is presenting. If a civil engineer picks up a piece of paper and sketches some plan of a building, that's not a model. That cannot be used by the civil engineer to ensure or provide evidence that their building will be good. It is just a drawing. So my work, and the work of my research group called RoboStar, is to develop notations, tools, and techniques that allow a roboticist to write their models in a precise way and with strong mathematical underpinnings. So that's an example. Again, I don't need you to understand the details of that, but it's an example of a model that you can write for a robotic software using our notations. Because it's precise, it can be backed up by a tool. Because it has mathematical underpinnings, we can be sure of the properties that we can deduce from the use of those models. So we are developing tools for these notations that we are defining. We are embarking on a 10-year program funded by the UK Research Council, the PSRC, and by the Royal Academy of Engineering, to a value of more than £5 million at the moment. And our remit is to specialize techniques, specialize the mathematical principles to allow us to use software engineering techniques in the area of robotics. So you have there a video with a demonstration of our tool as it exists now. There are very challenging and very exciting issues that we need to address in this robotic area. A robotic software does not run on a desktop or on a laptop. It runs on a robotic platform that influences and is influenced by the environment. And the environment is no longer the environment of a factory. It is no longer the environment that is static and well organized. There is a lot of uncertainty in the environment of our streets, of our hospitals, of our home, and that uncertainty makes the mathematics that we need to reason about this software we use in this context extremely challenging, but extremely exciting. So we are, in our group at the moment, moving to work and cater for the mathematical foundations to deal with the robotic platform, to deal with the environment. And the tool that's being demonstrated there, it can already cater for the software. So it can already, in an automatic way, directly from the models that the roboticists write, provide automatically reports like that that's shown there for you. Those reports, they are showing that for properties that have been identified as important for that particular software, it is showing that those properties are valid. And that's before we even started writing any line of code. We know that those properties will hold. Sometimes the report comes back and says, no, they don't hold. So again, before I wrote any line of code, I say, okay, there is a problem in my design. I need to revise my design, which is much cheaper than trying to rewrite code, right? And I get that feedback automatically. These techniques can also provide you with other important artifacts for software engineers. It can automatically give me the simulations. It can automatically give me the tests. It can automatically give me even a sketch for the code that I will eventually use. So this is the future that we see. As we evolve and we can cater for more and more aspects of a robotic system, our expectation is that roboticists will be able to provide consistent, good outcomes. They will get the recipes right and get for us good systems, good robotic applications that we can trust. They will never go back to be writing lines of code as their very first step. And in that situation, where we can provide evidence that we can trust the systems that are being produced, we will then be comfortable to have these robots around us, helping our elderly with day-to-day tasks, perhaps, interacting with our children, helping us in the offices, around the university, in our homes, everywhere. And in that context, the robots will always say yes. Okay? Thank you.